Right, this is the final part of part 1, and we are going to discuss something called the detail balance condition for effective stochastic processes. I'm going to explain what they are. And in this part, we started from the assumption of the canonical distribution from equilibrium statistical mechanics, and we used Hamiltonian time evolution to derive very non-trivial relations like the Jarzynski equality and the fluctuation theorem. Then we can ask, did we learn new non-equilibrium physics from this consideration? And of course, you can answer yes. These are universal, beautiful new relations for non-equilibrium processes. That's right. But you can be a bit skeptical and answer, well, not really, because these relations, especially in the setting that we discussed, are very, very general. They are too general and it holds almost all the time. And after all, if you examine, they follow from these two. So here in this part, in this final part, we are going to do the following. We start from the same assumption as before and follow almost the same logic as in the fluctuation theorem and derive something called the detail balance condition. What is this? Well, this is the essential constraint on effective description in the effective descriptions in terms of stochastic processes called Markov jump processes of non-equilibrium processes. Okay, so these were sort of goals, but this won't be a goal. This is just this will be the basis of our new approach, which we discuss in parts 3 and 4. Okay, so in that sense, this part is really a foundation for our further study. Okay, so to motivate, consider a Brownian particle in a potential. So consider a classical particle trapped in a potential with multiple minima like this. And we suppose that the energy of the particle is small enough that particle stays almost all the time in one of the minima of this potential. We label these potential minimum by this index jk. J equal 1, 2, 3, and so looks like that. And suppose that this particle is surrounded by many, many small particles which are in thermal equilibrium. For example, you can imagine that this particle is a plastic bead whose side radius is like 1 micrometer, which is trapped by an optical tweezer. And these small particles are water molecules of surrounding water. Okay. And then, as I said, this plastic bead is trapped by a potential, but there are many water molecules and they hit this small particle. And sometimes it gets some sufficient energy to climb up this potential wall and move to a different minimum like this. So with some small but non-zero probability, the particle may tunnel the potential barrier and jump to a neighboring potential minimum. Okay, and of course, tunnel is not a good word. This is not quantum mechanics, so it doesn't tunnel. Okay, sorry, it really climbs up and jumps. But anyway, this is what can happen. What happens in this kind of situation? So this is our assumption. Effective stochastic process for the particle is described by is obtained under this assumption. So we assume that the particle stays mostly near one of the potential minima and is almost in equilibrium with surrounding particles. And from time to time, it jumps to a different minimum in a stochastic manner. And these are justified in the situation where the potential barrier is much larger than the KT, the thermal energy. Okay, if KT is much larger than potential barrier, then it can go everywhere. But in this situation, our particle stays almost here, and from time to time jump to different minimum. Okay, and the question is, if when this particle jumps, are there any universal rules for this transition? And the answer is yes. That with this universal rule is called the detail balance condition. Okay, so we're going to examine this kind of transition from the minimum J to a different minimum K. Okay, so now we want to go to microscopic setting, description, and examine this transition. Okay, so the formulation. So by R and P, we denote the position and the momentum of the particle, Brownian particle. Okay, so R is in a finite box in R3, for example, and P is just the momentum. And VR, this is a potential for this single particle, and it has many sharp local minima, denoted as J equal 1, 2, 3. And by Sj, we denote sort of support of local minimum. So this Sj is a sufficiently large region, including the potential minimum J. Okay, and we assume that if J and K are different, then this support do not overlap. Okay, and now this is for the particle, and there are many other particles like water molecules, and this excess collectively denotes all the positions and momenta of water molecules. So this contains a lot. Okay, and this uppercase X is the collection of everything. So this describes the phase space of the whole system. And this is an important notation. By this chi j of x, this takes 1 or 0. And this is a characteristic function which examines whether the particle is in this support Sj or not. Okay, if particle is found here, this function is 1. If particle is not in this support, then it's 0. Okay, and since this depends only on R, I remark that this chi j is invariant under time reversal. And this star means that you flip all the momenta, right? Okay, so since it depends only on R, this is true. Okay, now these are notations. And also, we want to assume something about the Hamiltonian. This is our total Hamiltonian. It consists of the kinetic energy of the particle, potential of the particle, and this HSXS, this denotes the whole Hamiltonian of these water molecules. And this one denotes the interaction between the particle and water molecules. Okay, and I denote all these things like this, H tilde S of X. Okay, and I assume that this whole Hamiltonian is time reversal invariant, and I denote by T of tau the time evolution map determined by this Hamiltonian. I know I'm always saying this, but you can never, in general, you can never compute this time evolution map explicitly, but still we can derive something. Okay, now this is our important initial state. Okay, what is this? Well, this is called the constraint canonical distribution, and this is basically the standard canonical distribution with one constraint that the particle is near the minimum J. Okay, so here's the Boltzmann factor, that's the standard, but here this chi. Okay, so this one is 1 only when the particle is near this local minimum J. Okay, and this must be the normalization constant, so this is a definition. So this is a constrained canonical distribution. Probably this is a constrained partition function, and this is a constrained or effective free energy, which depends, everything depends on this J because you have this. Okay, and now this is the transition probability. We want to consider the situation that the particle is first at time 0, particle is here in this Sj. So it's somewhere here and in thermal equilibrium with surrounding particles. So the initial state is described by this Pjx, okay? Pj is this. So the particle is near the local minimum J, and it's in thermal equilibrium, okay? So this is our initial state. And then we want to consider the probability to find the particle near the minimum K at time tau, okay? So it was here at time 0, and it's here at time tau. So how do we find this probability? Well, this one does the job. So T tau of X is a time evolution. And then you examine by this chi function whether it is in here or not. If it is here at time tau, then this is 1. If it is not, if it is somewhere else, here, it's 0. Okay? So this is the precise probability that you are here at time equal 0, and you are here at time equal tau. Okay, here's one remark. If this tau is too long, if you let this tau go to infinity, then this one becomes essentially the equilibrium probability distribution of this case, and it depends only on k. It doesn't depend on j. So that was what will happen if tau is too large. But if tau is small enough, so that this transition probability is very, very small, it means that in this small amount of tau, particle doesn't travel much. I mean, it's almost here, but sometimes with very small probability, it's here or it's here. Okay. In this case, we can interpret this p tau of jk, p tau of jk as the transition probability from the minimum j to minimum k. Okay. Is this clear? Okay, so I note that we assumed here that the surrounding particles are in thermal equilibrium before the transition, okay? And this, I think, it may be justified if there are sufficiently many small particles. Of course, this particle that we are focusing on is not in equilibrium in strict sense. So in that sense, water particle may be affected by this non-equilibriumness of red particle and become slightly non-equilibrium. But when there are sufficiently many water molecules, we can safely assume that the surrounding particles are in thermal equilibrium. Okay, so this is an important point. But anyway, this is our definition. When tau is small enough, this can be interpreted as the transition probability. Then we want to derive the symmetry for this transition probability. So this is our initial state, restricted canonical distribution. And this is, I just copied and pasted. This is our transition probability. Okay. And now, okay, not now. I simply plug this in here, and this is our transition probability. Here's the Boltzmann factor. This says that the particle is near j at time equals 0, and this says that the particle is near k at time tau. And now we do this change of variable, but which you are already familiar with. So this is our initial state. We evolve it by time tau by this, and then take time reversal. We call it x prime. Then the Liouville's theorem tells you that dx prime equals dx, no Jacobian here. And also time reversal symmetry tells you this. This means that if you go and flip momentum and then you come back here, okay? I think you're already familiar. And this is a new one. This represents the energy conservation law, okay? And now here we are considering a system with time-independent Hamiltonian and no operation from outside. We only have autonomous time evolution. So of course the energy is conserved. So this is equal to T tau x. This is the energy conservation. But this T tau x is x prime star. And since, so this is x prime star. Okay. But since this Hamiltonian is time reversal invariant, this is equal to hx prime. So we do have this identity. So we plug everything in here. This is the same. This becomes this. And this becomes almost this with star, okay, by this. But since this one is time reversal invariant, so we can drop star. And again, we can put star here, and then this is equal to this. And this one by energy conservation is equal to this. Okay. And now we just divide this by zk, and you again put zk here. This is trivial. But if you look at here, now we have a transition probability. But in this case, if you regard x prime as the initial state, we are near k at time 0, and at time tau, we are near j. And so we are going from here to here. And here's the normalization. And so we do have the restricted canonical distribution here. So this becomes exactly the transition probability from k to j within time tau. So this is equal to this, and the same thing. So this is the this is a very non-trivial symmetry between the transition probabilities from J to K and K to J. Okay? And if you take the ratio like this, and this becomes the ratio of these, and so this becomes like this, where F is this effective or restricted Helmholtz free energy indexed by this potential minimum, index J. So this is an essential symmetry of the transition probabilities, and this is the detail balance condition. And in some case, this can be simplified. Here, this Fj, of course, Fj, Fk depend on beta, the inverse temperature beta. But in some cases, you can neglect this beta dependence. And then in that case, you call this Fe, like energy. And this takes this simpler form. So actually, we mainly use this form of detail balance condition. So when this kind of simplification is justified, well, I think there are many different reasons. For example, there are cases that we are interested in a very small range of beta, and within this very small range, the beta dependence of F can be neglected. In that case, we just neglect beta dependence and write in this way. That is okay. But there are different way of justifying this. Oh, but okay. Before talking about that, I have to make one important remark. Okay. As I said, this P tau, this is interpreted as the transition probability when tau is small enough. Okay? Tau is sufficiently small. Only when tau is sufficiently small, we can interpret this as transition probability. But this identity itself is valid anytime or for any tau. Okay, so if tau is larger, then this loses the meaning as transition probability, but still this is true. And especially in the limit where tau p is infinitely large, then this becomes something like the canonical distribution. Sorry, when tau is infinitely large, then this loses J dependence and some partition function-like thing, and this becomes something like this. Okay, this is the canonical distribution. It doesn't depend on J. It depends only on K in this way. But if you plug this in here, you find that this one only depends on K, this one only depends on J, and their ratio is precisely given by this. So in that case, in this tau, huge tau case, this has no meaning as transition probability, but this is still valid. But anyway, we are interested in the case when tau is small enough, and this is interpreted as the transition probability, and in that case, this is valid. Okay, and so well, you don't have to care, but let me briefly discuss one way of justifying this simplification. Okay, the idea is very simple. Here's the potential V, but we assume that this local minima are all identical. More precisely, there is one V naught R, and all these local minimum are simply translated copy of this V naught R. And of course, you translate it in this R direction, but you can also shift in the energy direction by adding your favorite energy for each different local minimum. And then for the particle trapped in this local minima, and every local minimum is the same, and they look the same. Okay, so that's the reason that we can make simplification. Okay, to be more precise, I assume that this HS XS and this is the Hamiltonian for water molecules, and this one representing the interaction between the particle and water molecules are translation invariant. And also VR is written like this. Oh, but I have to tell you this. So first of all, our J0 denote the center of the potential minimum J. Okay, and then and I also assume that this S0 S naught is center at the origin. And then, first of all, this support Sj is simply the translation of this S0 by our J0. And this VR, when R is in this support R support Sj, VR is precisely written like this. It's just the translation of V0 by Rj0, and here's the constant shift in energy. Okay, and if you assume this, then it's very easy to show that the ratio of Z becomes this, not necessarily the free energy difference. And well, it's very simple. So this is a definition of Zj beta, and here this is actually the same as chi j of x, but I denote it in more explicitly by using R. Here chi denote the characteristic function. When something inside is true, it's 1, and if something inside is false, it's 0. This is just a standard notation. And okay, by using this, Zj beta can be written precisely like this. And now I make a change of coordinate only for lowercase r, okay? And we use the translation symmetry for this one. And as for this one, by making this translation, you can write it like this. Or here it becomes like this. If you sit down and think, it's just easy. So this R new is R here. Sorry for sloppy notation. R new denotes R here, and this R old denotes R here. So this means R old minus Rj0 is in S0. That means R old in Sj, okay? And this one too. VR is written precisely like this. Okay, and you can justify this. And then if you look at this expression, and then J dependence is only here. And this is a constant, so you can pull this out and call the rest Z notes beta, and then you get this. Okay, from this, you find this. So this justifies this simple form of detail balance condition. Okay. Okay, so I want to generalize this consideration of detail balance condition to a more general class of models that we are going to consider in part 3 and 4 of this lecture. Okay, and as usual, so this x denotes the whole coordinate, the coordinate of the whole thing that we consider, and we assume that it's decomposed into x0, 2 parts, x0 and xs. Okay, and xs is again the huge surrounding environment, the coordinate of huge surrounding environmental system, like water molecules surrounding the system. And here x naught may be the coordinate of a single Brownian particle, but it may not be a single particle. Anyway, this simply denotes a smaller particle. It can be a coordinate of large system or a small system, whatever. But what we assumed is that this x0 is described by a potential which has, again, multiple very sharp local minima. Okay, so that is our assumption. And we are interested, of course, we are interested in the behavior of this system and treat this system as heat path surrounding this system. Okay. And one example is, of course, the Brownian motion, but here are further examples. Ionic conductors, which studied in chemistry, is a kind of conductor where conduction is current is carried by ions in a crystal. And unlike electrons in metal, they do not move freely in the crystal. They are sort of trapped by potential. And from time to time, it moves to a local minimum near the present position. So it's very similar, almost the same as our description of Brownian particle. But now there are many particles. There are many particles, and they are charged. So if you apply electric field, we can let them move. We can let them carry electric current, so on. So these are, of course, this is not the most popular system in condensed matter physics, but this is a very particular example in which this kind of idealization is justified. And we can also consider sort of molecular machine or like molecular motor studied in biophysics. And in this case, we consider a huge molecule which have several stable positions and move from one position to different position in a discrete manner. Or you can consider spin system, and actually real spin is a quantum mechanical object, and you have to use quantum mechanics to describe them, but you can think about sort of Ising's model-like classical system in which you have this kind of lattice, and on each lattice side you have a degree of freedom which you call spin, which may take up state or down state. And they are mostly in one of these spin configurations, and from time to time there is a spin flip and this configuration changes. Okay, so this is our basic assumption. X naught is mostly close to one of the minima and jumps to a different minimum stochastically from time to time. So this is a kind of system that we want to discuss in parts 3 and 4. Okay, and this is an important remark, but we study this class of system not because we are very much interested in ionic conductors. Okay, we are interested in many different systems, but we want to discuss general results and concepts in non-equilibrium physics. And to do that, this kind of system, which allows us to use discrete description, is theoretically very much suitable. It's very easy to study this kind of system with discrete stable state, almost stable states. So that's the reason we study this kind of system. Okay, I like spin system, but we want to study something which goes much beyond ionic conductor, molecular motors, and spin system. Okay, and we are going to develop our theory within this kind of framework, but what we learn there will apply to much larger class of systems. That's the important message. But anyway, so this is a simple single one-page slide, but this describes the assumption about X naught, and also this describes kind of systems that we consider in the latter parts of lectures, like part 3 and 4. So this is a very important slide, and let's proceed. So I want to discuss that I want to argue that detail balance conditions also apply to this kind of generalized systems. Okay, so this is detail balance condition in this case too. J and K denotes, now they denote a very complicated state. In case of ionic conductor, J denotes the single J denotes a configuration of all these particles. In a spin system, single J or K denotes a single spin configuration of the whole system. Okay, so from transition from J to K means configuration changes in certain way. Usually, there is a hop of single particle, or there is a flip of single spin. But anyway, J and K both denotes very complicated configuration of the whole system. Okay, but anyway, in such a complicated situation, I argue that detail balance condition is still valid, and the derivation is essentially the same. And I'm becoming very sketchy here. And again, we can consider a constrained canonical distribution where Sj denotes a set of states in which X naught is near the Jth minimum. Okay, and then we again define this constraint partition function, and with some simplifying assumptions, maybe the simplifying assumption is that this is actually Fj beta, but beta dependence of F is small, so you neglect or whatever, or we make a more detailed assumption. But anyway, we can safely assume in many cases that this is written probably approximately like this. And then I'm very sketchy. We can define the transition probability again exactly in the same manner as before. So it's this X naught is near the minimum J at time 0, and at time tau it's near the minimum K. Okay, and when tau is small enough so that these are very small, we can interpret this as the transition probability from J to K. And I have to assume again time reversal symmetry of the whole Hamiltonian, and again go through exactly the same derivation actually. We get this detail balance condition in this case too. Okay, So this is the generalization, and we're going to use this in part 3. Now we still have 3 pages, and I'm a bit tired, but let's continue. So now in these 3 pages, I want to discuss very important extension of the previous consideration of detail balance condition. We want to extend this to non-equilibrium environments. So this will be the subject of part 4. And if we extend this to non-equilibrium, actually, so we were discussing equilibrium environments here, okay? Because yeah, we were discussing the situation where, yes, huge surrounding environment is in thermal equilibrium. That was our assumption in this previous consideration. But now we want to consider certain non-equilibrium environments. In this case, detail balance condition will be generalized to something called the local detail balance condition. Okay. And first of all, this is a very important non-equilibrium situation. Consider the situation where our system is in touch with 2 different heat paths with different temperatures. This is really non-equilibrium. But I argue that even in this case, we have this symmetry for transition probability, which looks almost the same as the detail balance condition. But the difference is here. Here you have different betas, beta 1 and beta 2. And what we argue here is that when the transition, microscopic transition from the state J to K in the system takes place, we assume that the system interacts with only one heat path. Okay. Of course, you can think about much more complicated situation that both the heat path plays role, but if they are sort of separated like this, it's reasonable to assume that for some transition, only one of the 2 heat paths is relevant. Okay, so I assume that in this transition, only heat path alpha can be 1 or 2, plays some non-trivial role. And in that case, what you have to do is very simple. In order to analyze this kind of transition, you can, if only heat path 1 takes place in this transition, you can just forget about path 2 and consider the system, classical system, consisting only of path 1 and the system, and repeat the consideration that we did before. But everything is the same. We have a single heat path in the system, and everything obeys Newtonian mechanics, and then you get this, right? So if the system interacts with heat path 2 when this transition happens, then you forget about heat path 1 and repeat the previous consideration, then you get beta 2 here. Okay, so in this way you get this. Okay, so this is of course not the low detail balance condition with this non-single beta, but with this heat path dependent beta, we get a local detail balance condition. Okay. And this will be of course used when we discuss like problem like heat conduction from one bath to the other. Okay, so that is one extension. So we are done, okay? I told you what is the extension and I proved this. Oh, but here, again, we are making a very non-trivial assumption that both heat paths are precisely in thermal equilibrium all the time. And of course, this may be unrealistic if the 2 heat paths interact too much and then they become sort of non-equilibrium. But if these heat paths are big enough and this interaction is small enough, and then we can safely assume that they are always in thermal equilibrium. So that is the limit we treat. Okay. So anyway, in this limit, we can derive this non-trivial relation for the transition probabilities. Okay, so 2 more pages. Now we consider a different type of non-equilibrium condition. Okay, and suppose that we have a system of charged particles and you apply electric field, and then there are the current of particles, flow of particle, and you want to analyze this. But in order to do this, what you usually do is to put particle baths at the 2 ends of the system, And of course, you want to apply electric field. So the particles will be supplied from this particle bath, and then it goes into this particle bath. Okay, and then you will have this non-equilibrium flow of particles. Suppose that you don't have particle bath, and simply the system ends here, and if you apply force, then you get an equilibrium situation where you have many particles here and small number of particles here. Okay, so in order to have a constant flow of particles, you must have particle bath at the two ends of the system, and then you apply electric field. But if you do that, of course, then you have to worry about the design of particle bath, and you have to worry how the system and this particle exchange particles and so on. So that's, of course, we can do that. We don't do that in this lecture, but we can treat such a setting within the same framework. But anyway, it becomes tedious. There is an easier way. You apply a constant external force, and you also impose the periodic boundary condition. And so this is connected to here. Okay, so suppose that this is gravity, and so you fall. Whoa, you go down. But this is you take periodic boundary conditions. So you appear here, and you keep on dropping like this. Okay, so here's a better picture by Penrose. So here's a weird staircase. You start from here, and you go down the stairs. You go down the stairs, go down the stairs, go down the stairs, go down the stair, and you come back here. So you can just keep on going down the stair forever. Okay. So, and of course, you know that this is impossible, and you cannot have periodic boundary condition that connects here and here. And so this is impossible. And that, in other words, this F is, this is a constant external force, but it's not only external force, it's a non-conservative force in the sense that it's not expressed as a minus gradient of some potential. Okay, and so that kind of weird force, unrealistic force, is called non-conservative force. But anyway, consider this constant non-conservative force, and you can write down the Newton's equation. You can write down Newton's equations for this case. You cannot write down your Hamiltonian because this F does not come from a potential. But you can write down Newton's equation in this case. And this is Newton's equation for the particle. Also, we are considering this single Brownian particle. I'm sorry, did I say this? So this is Newton's equation for this Brownian particle. And so this part is the standard gradient force. This is a force from this potential. This is a force from surrounding water molecules. And plus F. You can write this Newton equation. This describes this non-conservative force. You can never write this as a gradient of potential, but anyway, you can write this. And you can write this kind of equation, and you can study this kind of dynamics. And you can study non-equilibrium states or non-equilibrium steady states realized by this kind of Newton's equation. Okay, so that's what we are going to do in part 4. Okay, and I emphasize that this is a very unphysical setting, but still, for the reason I explained, this is often used to study the current induced by external electric field. And because by doing this, you don't have to be bothered by complicated physics that emerge at boundaries. Okay, so this is very artificial, but this, this allows us to study the effect of, this allows us to study non-equilibrium state with particle current in a theoretically easy way. Okay, now, so this is an introduction of this very important unrealistic situation, so please keep this picture in mind. And I argue that in this case, we can rather easily extend detail balance condition. In this case, a detail balance condition is extended to this form of local detail balance condition. And this part is exactly the same. And here we have additional part, of course, coming from this non-conservative force. But you can easily find that this, of course, encourages jump from here to here, right? For example, suppose that F is a force like this, pointing this direction, and suppose that J and K are like this, okay? And then you can compute that this becomes, okay, if this is F, 0, 0. This is something like minus delta R 0, 0, where delta R is a positive thing, and the inner product is minus delta R. So everything becomes a positive number. Okay, and anyway, you see that this term encourages the hop from left to right. Okay, not and discourages the hop from right to left very naturally. And I argue that this is easily derived by using the previous result about detail balance condition. How do you do this? Well, I said that this kind of situation can only be described by this Newton's equation, and you cannot describe this dynamics by Hamiltonian equation, Hamiltonian dynamics. That's true if we consider the time evolution for sufficiently long time. But we are only interested in time evolution for very small time, okay, small time tau. And then when time is small, this particle is, well, almost here, stays here. And with very small probability, it's here. With very, very small probability, probably it's here or it's here. But we can safely neglect the possibility that it's here or here. So this means that we can only concentrate on this finite part of the system and consider this dynamics. But then if we are only interested in this part, then this constant force can be described by the standard potential, a standard force coming from the potential. This can, you consider this potential, and then this can be described as the minus gradient of this potential, okay? And of course, if particle goes beyond here, this potential doesn't work, but our tau is very small, so this description in this local potential is enough, okay? So this is this picture. So what we want to consider is this situation. You have this potential and non-conservative force. But our time, if tau is short enough, this is equivalent to this situation where you have no weird we only have conservative forces. We have no non-conservative force, but we have this modified potential. Okay, this describes this F. And we can simply, but this is a standard potential. So we can simply repeat our discussion for detail balance condition and to derive this new local detail balance condition. So this is, I explained the same thing here, okay? And everything was for a single particle, but you can easily find that the same extension is possible multi-particle systems like ionic conductors. That's very realistic situation. So you want to apply electric field to ionic conductors. And of course, periodic boundary condition is not realistic. So if we take ionic conductor, apply electric field, and impose periodic boundary condition, and then we get this description. Okay, yeah, probably when you first saw periodic boundary condition as a freshman, for example, you thought that it's a very weird artificial boundary condition, and you might have asked, well, what is this? And in one dimension, probably you can understand that as a system becoming a circle like this. But in 2 dimension or in 3 dimension, how do you imagine that? But after sometimes I think you got used to it. In many calculations in like quantum mechanics or statistical mechanics, you simply use periodic boundary condition to make the problem easier, and then you don't have to worry about weird things happening at the boundary. And you basically get the same result by using this periodic boundary conditions. But in this case of constant force, periodic boundary condition is essential. Okay, as I said, if you take normal boundary condition, then you don't have anything like current, steady current. Everything goes to the right, and that's it. But if you have force and periodic boundary condition, then you get non-vanishing current, which goes on forever. So in this case, taking periodic boundary condition is something very essential. It's not a technical assumption. Okay, so that's all for this part.